The next speaker is Dario Gil, and Dario received his PhD from MIT, and he's since had a very illustrious leadership career at IBM. He is now a leading technologist and VP of AI and IBM Q, which is their commercial quantum computing program, and he'll give a talk on the physics of AI.
Thank you very much. And let me begin, Dimitri, by thanking you for, you were my thesis committee, when I graduated from MIT. And just on behalf of IBM, I put the picture because you've had such a long history of collaborating with us, and I hope it was also part of your home, right, of intellectual home and being with us. So a big thank you for that wonderful collaboration. The talk, the comments I'd like to share will have some connections to the wonderful presentation that Philip did this morning in terms of the importance of bringing logic and memory together in the context of AI. And also, in Dirk's presentation, and I'll get a chance to make some comments as well in the progress of quantum computing and the relation of actually quantum computing devices and machine learning. So I'll begin by, a lot of the foundation and give a little bit of the context of why there is so much excitement going on right now in the field of deep learning specifically, and AI more broadly. And in some ways, the root of the intellectual root of the current progress dates back, as early as the work of Ramon y Cajal and others, where, the scientific community came to realize that we had the presence of these neural networks in our brain. Now, I'll do a plug for Ramon y Cajal. There's going to be a wonderful exhibit at the MIT Museum starting next week of his original drawings. And it was in New York City, the last few months, and he's now going to move here. So I highly recommend you see it. He was a wonderful illustrator in addition to being an amazing scientist. And it was with no more than this biological inspiration that there was a generalization that took place starting in the 1940s with simpler forms of artificial neural networks that later have become what we understand now as the deeper networks that get used in deep learning. But there was this abstraction of going from the concept of neurons, illustrated by the circles there, the connections on multiple layers, as read in this neural network that you read from left to right, and that the connection between these neurons were a form of synapse, right? And today, the basis of training these kind of neural networks is learning the weights and the degree of connectivity that we gotta have between those neural network structures. Now, with the advent in the 1980s of an algorithm called the backpropagation algorithm, there was a greater efficiency with which we can train and find the appropriate weights for these neural networks. But it was the combination of those advances, and as is well known, advances in computing power, particularly the utilization of accelerators like graphical processing units and GPUs, that really created a fundamental transition point in the field. So in 2012, to be very precise, if you look at the example of the accuracy with which classification could be implemented on ImageNet, on the ImageNet data set, you saw the biggest improvement in accuracy in the history of the computer vision field. And what has happened since 2012 until today is that basically the entire field of computer vision, to give an example, has been transformed to implement deep learning-based techniques to perform the task. Now, the net result of this is that a narrow form of artificial intelligence that exploits these properties has begun to work. And that is the progress, that is that direct consequence of the progress that you're seeing in the areas of language translation or speech transcription or even simple forms of natural language processing, et cetera. It is the fact that finally this old idea that had been realized theoretically and conceptually for many decades intersected with enough data sets and enough computational power to start tackling some of these problems. And people have really caught on to this. And I think you're all witnessing the fact that in every discipline and every institution all over the world, people are asking themselves the question, how should I exploit this capability? How should I use AI for my field and discipline? And the students get this. And we're seeing record level of enrollments on classes that, frankly, a decade ago may have had 50 students taking introduction to machine learning. And you're seeing over 1,000 students at Stanford. Maybe Philip will have the latest numbers on that. And you can see the progression of what has happened at MIT as well, right? So this is it's been very exciting to see. Now, that's a narrow form of AI. I just wanted to say a few words about what the evolution of the field may look like in the coming years and the connection to physics. At the other extreme of the equation, we have what is known as artificial general intelligence. That's many, many decades away. It's not, we don't have any good clarity as to how to get there. There's different approaches people are pursuing. But what I wanted to share is kind of like the transition that we have to make between this narrow form of AI that has begun to work, where we see superhuman accuracy for very specific tasks, to a broader form of AI that will have to have a set of attributes that should include the ability to have a single network that can perform multiple tasks and work across multiple domains. Today, the way that deep learning networks get implemented is you try to solve a task, and when you want to solve another task, you basically have to create another deep learning network, and on and on and on. Now, as a user, you may have the illusion that these things work together, but it's just a user interface illusion, right? But the fundamental behind the scenes is that they're all distinct. Multimodality, a more distributed form of AI, including AI at the edge, a more explainable form. So if I were to summarize in kind of like one general slide, some of the key areas where things need to go is that we need to make AI that is much more explainable and a deeper understanding of what is happening inside the networks. Security, if you have followed the progress in the field, a lot of these neural networks are subject to adversarial attacks, and you can get, sort of like with small perturbations into the input signal, you can actually fool the systems to do something very bad. And then there's the issue also of bias in systems and how we're going to make sure that we're not perpetuating biases that exist in society because we're encoding it in the historical data that we have in a neural network that then we use automation to scale out. That would be a very bad outcome for the use of AI. We also have to blend the two historical traditions in AI, the logic and knowledge representation part of AI with the learning part of AI. And some of the most exciting work going on in the field of AI right now is in being able to bring those things together. Because frankly speaking, that is the path to be able to learn with less data. If we want to learn with less data, we have to have prior knowledge. One mechanism of that is to learn in one network and transfer the knowledge to another network so that we can learn with less. But another one is to actually have knowledge repositories and be able to reason over that data and to implement logic over that data and bring it with learning. But today, I want to talk about what we refer to as the physics of AI, of what is the hardware roadmap of the devices beyond GPUs and beyond CPUs for inference. So the roadmap that we are pursuing at IBM and with our collaborators has a set of distinct dimensions. One is to say, beyond the GPU, how do we implement approximate systems and approximate forms of computing, given that these kind of neural networks are very tolerant to error. And the level of precision that we need to execute this is not, we don't need to use floating point operations as an example. I'll say a bit more on that in a minute. The second one is how do we actually implement new materials and particularly use existing devices that we may have, like non-volatile memory, now in the context of logic, right? Not just as a memory unit, and how we may even invent new devices that have unique properties for the field of neural networks. And then I'll make some comments also about a nascent field at the intersection of quantum and machine learning. So this is a roadmap that we have observed and a forecast and a projection. We believe that the field is accelerating, meaning whatever metric you want to use, but let's say the cost of building a neural network model is basically going to improve at about 2.5x per year. So about 1,000x performance we can expect over the next decade from where we are today with conventional GPUs. And so I'm going to talk sort of in the beyond GPU regime. And one advantage that we need to exploit is that actually the form of computation that we need to perform is very simple, relatively speaking, right? So we don't have to implement a universal form of computation like in a traditional CPU. But here we have this function that we have to do, this multiply accumulate function that happens on each neuron. Remember, every neuron is connected to, in a fully connected network, to every other neuron. We have to do the multiply accumulate. We have an activation function. This is a nonlinear function. That is what allows the neuron to trigger, right, and go and tackle the next neuron. And then during the training phase, we have to do a weight update, right, which again is a multiply add function. That is how we update the weights in the neural network. So those are the core functions we need to implement, right? So one reasonable first step in this roadmap, the purple lines indicate sort of like the known roadmap of GPUs, right? So here I'm talking about ideas and technology that would extend it beyond current GPUs. So one idea is something that we had started exploring as far back as 2015, was obviously reducing the precision of the computation. And we had demonstrated at the time that you can implement equal levels of error rates when you implemented, let's say, a 14 bits of precision instead of floating point. Since then, there's been many demonstrations going down to 8 bits, 6 bits. Even people are exploring going down to 1 bit, right? Which is pushing to the limit. And, but we recently just published, the team in Zurich and IBM Research Zurich just published in Nature Electronics this idea of a hybrid mixed precision linear algebra solver, where we're using an array of about 1 million PCM elements that is coupled with a digital processor. And what you're doing there is that intrinsic multiply accumulate function is happening in the PCM array. So you're getting a lot of efficiencies by doing the computation at that level. But then when you need a little bit more accuracy, you iterate over the digital system that you have available. And what you see on the left-hand side is that there was a system of 5,000 linear equations that would solve implemented in this system, and that the number of iterative refinements can get you to the level of error rate that you want. So this is kind of an exciting direction to get the best of both worlds. When you need more precision, you iterate a few more loops with the digital loop, but if not, you get the advantage of sort of the matrix multiplication that happens inherently with this array of non-volatile memory elements. Okay, so that's a good efficiency improvement that you can get once you have trained the system. But what if we wanted to improve the training itself, right? What else can we do to do that? So here is, in connection a little bit with what Philip talked this morning, one of the things we would like to do is not to have to go out to memory to be able to either fetch the weights, right, or retrieve the weights. But can we bring logic and memory together in the context of a neural network? And this is, again, an old idea where you can implement, in this case, let's say we take the 2 first columns of the neural network. The first column represents the peripheral circuits here on the left-hand side of this systolic array. And then the second column of the neurons are now in this row, right? So basically, as you all know, what you can do is you can send variable voltage pulses that go into it. And when you read this column, you automatically, right, get the multiply accumulate function for free, right? So that's kind of like the whole idea. But the point here is that now in those unit cells, we want to implement a form of memory that allows us to store the weights of the neurons that I'm learning, okay? Now, what is different from a traditional memory cell is that we don't need to just have 2 states. We need to have incremental values. So let's say, as an example, I may have to have 10 or 100 states to be able to store weights like 0, 0.1, 0.2, et cetera. So that's one characteristic that's different than a memory cell. It can be slower. I don't need to do nanosecond level switching, like thousands of nanoseconds could be okay. The high-low transitions could be many orders of magnitude different. But there's another very important aspect of it, is that the switching should be symmetric, ideally, because I want to move my weights up and going down with symmetry. Right? And that's not true in a memory element. And there's many ideas that are being explored here. So for a number of years, we've been working on non-volatile memory demonstrations for these neural networks. And this is an example of using PCM as a mean to implement the training of a neural network. What I showed you before was about now, once you've trained it, how to use it for inferencing, right, for the calculation. And the good news is that now, after a number of years of work, we're demonstrating like similar levels of accuracy performance in terms of implemented with a PCM-based neural network array, but that it has 500x energy efficiency improvements compared to what you can do with a GPU. And then the final step that you can imagine is the PCM switching, as we mentioned, is non-symmetric, is what would be a device that is symmetric in its switching behavior. So there was a paper that was also published a few years ago on an idea called the RPU, the Resistive Processing Unit. And what the team did was a really nice piece of work, was to take the properties and the characteristics of what you need for machine learning and map it to a set of parameters and values that one would have to achieve from a materials and a device perspective. So kind of like to set a target for the community to say, can we create this device with these properties? And one of the key properties that is very essential is the symmetry of it. And here's just a recent result to give you an example of being able to engineer a material in which we're using a resistive RAM based on hafnium oxide as part of the element of it, where what you're seeing here is that the switching behavior of this memory element now is symmetric, which is going to be a very fundamental property to realize the full vision of implementing analog devices for both training and inferencing in the future of deep learning architectures. So let me switch and just spend a few more minutes telling you about now a different perspective of it and what we refer to as the physics of AI. So one was this analog story for AI, but the other one is how can quantum computing impact the field of AI? This is one of the quantum computers at our T.J. Watson Research Laboratory. Incidentally, let me just say that, they're some of the most beautiful computers that we have ever built at IBM. This is inside one of our cryostats, and what it looks, the wires that you see are the superconducting coaxial cables that send the microwave pulses to the quantum processor that sits at the bottom of this canister and operates at about 15 millikelvin, right? So we use superconducting technology. I just want to also highlight that, finally, after many decades of work, quantum computers are becoming real. This is just an example. We have 3 online quantum computers available for free to anybody to use in the world. This is an example of executions in our quantum computers in just 5 days, about a month ago, to give you a flavor for the number of people using now the system. We have over 80,000 users who have run 4 million experiments, and there have been over 70 publications that have been generated using our quantum systems, right, experimental ones. So we use, superconducting qubits. It's very specifically, we use a transmon qubit, and it's a Josephson junction that we use as a nonlinear inductor to implement this, what Dirk talked about, this Divincenza criteria of being able to create a ground state and an excited state that we can have precise control over. And we couple the qubits through microwave resonators, and that is what allows us to create the entanglement between these different qubits. But what I wanted to do is just briefly share with you a very recent result of using this kind of quantum system for the purpose of classification. Now, the set of applications that we can do with quantum computers, one of it is chemistry. That was the original proposal of Richard Feynman, and we've demonstrated recent work as well, simulating molecules using a quantum computer. Once one has a fault-tolerant universal quantum computer, you could implement things like Shor's algorithm, right? But that's ways to go to be able to do that. But today, I want to tell you a little bit more like a heuristic approach that is not based on theory to try things out in the field of machine learning. And what I like about that is that the field of machine learning in its own right is a very heuristic-driven approach. And the general idea is that a lot of the tricks that we do in AI is we take an input vector, input state, we map it to a high-dimensional state, and we try to find a hyperplane that classifies and separates things. And we use that for classification. We do that through a neural network, but now, thanks to the quantum computer, we can access a high-dimensional space that can be fundamentally different than what you can do in a neural network, right? So the Hilbert space that is available to us in a quantum computer, it is just different in nature, and to what degree can we exploit the properties of that space to do classification. And just again, as a simple example of why dimensionality and classification are connected, take the example on the left where you have a set of dots. Some are dark, some are light. And in that example, you can see that there's no linearly separable way. If I just have one line that I can draw, there's not a single line that I can draw to separate the dark and the light. But we know that if we curve that line, right, increasing the dimensionality of it, now we can find a simple line that separates the two. Take that idea and just generalize it to many, many dimensions, right? That's a lot of what takes place in AI today. So here, what we're going to do, I'm going to show you now the results of an experiment. On the left-hand side, that's the data set that we're going to use to train. We have 2 types of things. We have golden dots and dark dots, right? And we want to build a little machine that can learn the 2 different kinds of dots. So in the phase where I have training, this is, I know what the answer is. This is a supervised form of training. So here, I'm going to use a quantum computer, and I'm going to use entanglement to encode many different attributes from this space, from this two-dimensional array of data points. And in the end, I want the system to say they're either gold or they're black. So what do we do here? In the end, that's the function I'm trying to learn, right? So when I put new dots in the, say, golden area that I've never seen, I want it to say it's a golden dot. And when it ends up landing on the black area, it's a black dot, right? But I don't know a priori what that function is. I only had the sample data in there. So the way you implement this is that you prepare the quantum computer in a superposition. Then we use entanglement to be able to map the training data into a quantum feature map. And the idea is that the feature map that I have available in the quantum computer would be exponentially costly to replicate classically. That's the idea, right? That feature map is fundamentally different than what I can implement cost effectively with a classical computer. And then the next step is I train the quantum classifier by updating the quantum network, right? And that's the training piece of it. That will be the equivalent of learning the weights in my neural network. So here's the result of it. Now I have data to be classified. This is data I have never seen. And the result that we've demonstrated experimentally very recently is that the exploitation of this property of entanglement, which is costly to replicate classically, helps me improve classification accuracy. So this is kind of exciting because this doesn't prove that I can do something that I couldn't do classically yet. But what it says is that the property that I know is very hard to emulate classically, is helping me to improve classification accuracy in machine learning. So as I grow the ability to exploit that property more and more, and at some point I cross the point where it's not easy for me to implement that classically, the hope is that we can find classes of problems in machine learning that I couldn't do classically efficiently. So I'll just close to also celebrate and appreciate the wonderful partnership that we have established with MIT to shape the future of artificial intelligence. We launched last September the MIT IBM Watson AI Lab, and this is a commitment, the largest commitment we've ever made in the 107-year history of IBM, right, to a university, and to be able to do something really fundamental to shape the future of AI. We have defined 4 major areas in terms of pushing the boundaries of algorithms, the physics of AI, that was the nature of my talk, of how do we continue to advance that, applying AI to industry, and enabling and making sure that the technology you create is something that generates shared prosperity. And what I'd like to say is that it's been an enormous level of enthusiasm, and I'll just point out that in this field of the physics of AI, just, these are not meant to be read, but just to see just the sheer number of proposals and creativity that is coming from the community, from the IBM research community and MIT community, on thinking of ways on how we can continue to advance the field forward. So that's something enormously exciting. And with that, thank you very much.
So I can tell Dario is in the leadership role, very much attuned to the time frame of the talk. We do have time for some questions. We do have a break from 3 to about 3:30. Lisa will give her talk at 3:30, so please be back a little bit before then so we can start on time. But we do have time for some questions for Dario. Jeff?
Yeah, great. Thanks very much for that talk. In the earlier part of the talk, you talked about how today's networks are very sort of specialized. You need a different network for every single application. And that's even with networks that are implemented on GPUs and sort of a general purpose digital architecture, which can be rather readily programmed and then run to run inference. Now these analog networks that you talked about strike me as being even more difficult to generalize. It's even hard to figure out how to design a chip which is easy to program and run the data through in the same chip. So could you comment a little bit about how you imagine those kinds of architectures could be made more generalizable? Or can they? Maybe you agree with me that
Yeah. So in the versions that, in what I presented there, it was tackling the very specific problem of just addressing the current supervised form of deep learning, right? Let's just say that, right? So for well-defined neural network structures, how can I achieve orders of magnitude improvement in the training efficiency or the inferencing efficiency by using analog devices. So that's it. But the question you're asking is right, is like, what is the nature of that network structure? And what are different ways to connect them, to have networks with memory or without memory, right? To be able to allow them to learn more tasks, right? And share, because basically the idea is like, if you have very fixed weights, okay, they may perform that task very well, but when I implement a new task in the world, you face the issue as you tweak them, you face the issue of catastrophic forgetting, right? And now you lose the skill in that other way. So we need, in general, independent of the whole analog story, we need neural network architectures that are much more tolerant to be able to inject noise in the system and move from one state to another without this issue of catastrophic forgetting. The question that you ask is a very good one, is as those architectures develop, is the implementation that one does on an analog system, right, too confining or not, right? So we know that it's not for a broad class of, LSTMs, neural network, deep learning systems, reinforcement learning, a whole class of problems that are important today. We know that we can do it that way. So that's promising. But as we move to more, sophisticated forms of machine learning, that's an open question, because you could imagine we could create some architecture and connectivity that is not well implementable in that fashion. So that's the sort of balance that we got to strike. But for the stuff that gets used today, all over the world, it would provide a lot of value.
Go ahead.
I have two questions. My first question is, you talked about the phase change memory. How many times can you program it? Because apparently you're going to train it multiple times. So what's the endurance? And my second question is related to your quantum computer at IBM. How much power are you using to keep it cool? And is it even worth it to keep it cool?
Well, it's definitely worth it to keep it cool.
I mean, the amount of power you're spending to keep it cool.
Actually, cryogenics has improved tremendously. The stability and the amount of energy that you need to be able to keep these systems operating continuously is very modest. So it's not, my point is it doesn't take, it's just like a dilution refrigerator, and you have a gas tank, and you recirculate these helium, helium mixtures and so on. So it's very reasonable in what needs to be done. So it's not cost prohibitive on that question. And at the level of insurance, it would, of endurance of phase change memory, it would depend on the applications, right? But we certainly believe that you can achieve 10 to the 8, 10 to the 9 cycles, even higher numbers than that. So depending on what context you're using and what is the lifespan of a GPU today, right? I would say in generally they'll get replaced every couple of years or something of that sort. I don't think people are planning to use a single generation for a decade. So again, it's within the scope of what is realistic. The issue has to do more with the symmetric of the switching behavior of it. Ultimately, you don't want this transition from amorphous to crystalline. The lack of symmetry is a problem. So while the first generation is using a PCM to do things like that, we really need to evolve into something that has the right properties for these neural nets. Carl.
I think of quantum computing as a future technology, and I'm wondering, neuromorphic was on the slide at one point. I'm wondering what your thoughts are about neuromorphic. Is it more advanced than quantum? Is it less advanced than quantum? Which is going to happen first, neuromorphic or quantum computing?
Yeah. It's a good question. So the neuromorphic piece. So if you look at implementations, and we've done a lot of work on that, using STDP or things like that, the issue is that it's proven that you can do really sophisticated things with very low energy consumption. The issue is that do you really have an ecosystem and that implements the algorithms that have been proven to work, right? So the problem with it is that there's no equivalent of the deep learning sort of level of adoption with STDP types of algorithms, right? So until that happens, until there is more progress in demonstrating, right, that the algorithmic implementations is inherently better than what you can do, right? Yeah, I'll be consuming more energy and so on, but unless you achieve equal levels of accuracy, and you start doing things you just simply couldn't do, perhaps with time series data, that's promising. I think that there's an inhibitor of adoption, right? Ultimately, I think we'll have to go that way, specifically with this time dimension, right? I mean, the kind of neural networks we implement today are not very good to deal with time. And they're much better dealing with batch processing of information. So perhaps that's the angle, right? Some kind of like continuous learning at the edge where low power is required and a time series, maybe that's the path for insertion.
We have maybe time for one more question before taking a break. Any? If not, let's thank Dario and
Thank you.
everybody at the